So moving on to the first question that we have. A student measures the refractive index of oil. Oil is poured into a semicircular transparent plastic container as shown in figure 1.1. The container is placed on the top of a 360 protector as shown in figure 1.2. Alright, then we can see both of them. The line AB shows the position of the flat side of the plastic container. The ray of light is incident at the midpoint AB with an angle I equals to 30 degrees. As we can see from here, angle of incidence is 30, because if you start from here, from the normal, that would be 10, that would be 20 degrees, that would be 30 degree 10, 20, and this one would be 30 degrees. State one property of the oil that is needed to ensure the experiment works. Oil has to be transparent. Otherwise, we won't be able to see what happens to the rays of light, or what happens to the angle of incidence, to the angle of refraction, if it is not transparent or not colorless. So it must be transparent, just like the glass block. On figure 1.2, measure the angle of refraction R of the light in the oil. The angle of refraction needs to be measured. So angle of refraction is the angle between the refracted ray, this one is your refracted ray in this situation, refracted ray, and the normal line. Alright, the normal line is the line perpendicular to the surface. So this one line would be the normal line. And what is the angle? So 0, the starting one from the normal would be 0, and then you have 10, alright, and then 20, this one exactly would be 20, and then you have the next line is 22, but you have in the middle of 20 and 22, so that'll be 21, and you got to be precise with it. So angle of refraction is 21 degrees. The unit is already there, you don't need to write it. So when the angle of refraction incidence was 30, the angle of refraction was 21. We can fill in the table. Complete table 1.1 with your values of R from A to. We're done with that. On the grid provided in the figure 1.3, plot a graph of R on y-axis. This is the most important thing, that R has to be on y-axis. I mean, I can write over here, this thing goes on y-axis, and angle of incidence goes on the x-axis. I goes on the x-axis, and you need to ensure where do you need to start the graph from. Do you have a choice? No, you don't. You have to start it from 0, 0. And what you need to draw is the trickiest of them all cases, curve of the best fit. We have the first mark for just representing the axis. You know nothing about the graph, forget it, just represent the axis, you get 1 mark. So angle of incidence on x-axis, and that is measured in degrees. Alright, we just look it from here. And angle of refraction on y-axis, and that too being measured in degrees, or you can write /degrees if you want to, otherwise we are fine with it. Okay, and then what do we have? Now we need to start plotting the points. The first point that we have is 15 against 11. 15 on x-axis, 11 on y-axis. Now first we need to scale the axis. So we have to start x-axis from 0. The first one has to be 0, I mean they have restricted, and we have to reach all the way to 70. So it'll be fine if we do something like this. 10 after next 10 lines, 20, next 10 lines, 30, next 10 lines, 40, next 10 lines, 50, next 10 lines, 60, next 10 lines, 70, and next 10 lines would be 80. Y-axis has to start from 0 all the way to 45. Let's consider 50. So 10, after next 10 lines we have 20, 30, 40, and 50. Alright, you don't even need to write all the values, but just for the sake of convenience, I'm writing all of them. So first one is 15 against 11. 15 on x-axis against 11, so it would be right over here. Alright, in the middle from here, and 1 point, 1 box above, it'll be 15 against 11. Now with the first one, then we have 30 against 21 would be over here. Alright, you can draw dots even. Let's draw dots because my pointer is already quite thick. 11, 12, 13, 14, 15. Yeah. And here. Then we have 45 against 31. 45 against 31 would be over here. And then we have 45 against 31. 60 against 39. 60 against 39 would be over here. One line below 40. Then we have 75 against 45. 75 is in the middle of 70 and 80. So this line was 70. 1, 2, 3, 4, 5. 70 against 45. 1, 2, 3, 4, 5. 75 against 45. Yeah. 75 against 45 would be here. So this is the situation that we have so far. This is what the points look like once they are plotted on the graph. Now the last part is to draw the smooth line, smooth curve of the best fit. Now this is the most difficult part. So I'll try to draw. It's kind of tricky here on the touchpad, but I'll draw anyway. So smooth curve of best fit means all the points may not necessarily be on the curve. Alright, you don't have to change the direction in the middle of the curve just to ensure that all the points are on the curve. No, it has to be a single arc, single freehand arc, and if some of the points are not on the curve, then the points below and above the curve should be equal. Too smooth here, but once you draw it on the sheet of paper, it would be smooth. And the other thing is you draw a very sharp curve. Right, it has to be sharp, not a thick one, because if it is a thick curve, it occupies more than one box. Right, so you gotta be careful with it. The curve is smooth, the curve is sharp. Anyway, describe the relationship between I and R shown by the diagram. What it shows is if you increase the angle of incidence, the angle of refraction also increase. Alright, They are not directly proportional to each other because it's not a straight line. But if you increase the angle of incidence, the angle of refraction increases. I mean, you can also find from the table. For 15, R was 11. You increase the here you increase the angle of incidence to 30. It was 21. At 45 it was 31. So it is being increased. So as I increases, R also increases. And if you have the understanding of the angle of incidence and the angle of refraction, you will realize that this relation is actually fine. Because you increase the angle of incidence, the angle of refraction would increase, and at a certain limit, the angle of refraction would eventually become 90 degree. That for that angle of incidence, we call it critical angle if the ray of light is entering from dense medium to less dense medium. But in every case, you increase the value of I, the angle of refraction would also increase. Use your graph to find the value of R when I equals to 50. So it'll be like this point over here. So 31, 32, 30. We can call it 34. Appears to be 34, yeah. One line below 35, 34 degrees. Unit is already there. No need to write degrees again. Need to find the angle of need to find the refractive index. Formula is there, just like I told you in paper 4. We do have all the formulas, so all we have to do is to insert the values. So sine I, let's take any value from B3. Which one is B3 anyway? 50 against 34. Sine 50 divided by sine 34. Then we hit it on the calculator, and it will be into SF 1.3 or 1.4 something. You can hit it on the calculator. I mean, the answer would be 1.3 or 1.4 something, and it has no unit. And how do we know we need to write two significant figures? The raw data is in two significant figures. So they haven't mentioned that it has to be in two significant figures, but what they have stated is it has to be in appropriate number of significant figures. So you got to find it out by yourself, that how many numbers should be, significant figures should be there. Anyway, on to the next one. On figure 1.4, sketch the graph of sine R. Sketch the graph when sine R is plotted against sine I. No calculations are required. As the angle of incidence increase, the angle of refraction also increase. So it has to be a straight line. Through the origin, and it has to be a little bit closer towards sine I axis. And how do we know it has to be a little bit closer towards sine I axis? Because the values for the angle of incidence are always greater in this case than the corresponding values of angle of refraction. Like angle of incidence was 15, angle of refraction is less than 15. Or try any other one. Angle of incidence is 60, the angle of refraction is 39. It's less than that. So the graph has to be closer towards sine I, because those values are greater than the values of sine R. Then we have another one. Suggest one reason why the practical method used in this investigation might not give an accurate value of n. Curve of best fit. Curve of best fit drawn inaccurately, because we obtain the value of angle of refraction from the curve of best fit. And if there was some error in that, your value of sine I over sine r, the ratio would be changed, and the angle of and the refractive index would be different. A student investigates the cooling of water. The apparatus used in figure is shown in figure 2.1. The student pours 200 cubic centimeter of hot water into 500 cubic centimeter beaker, places a thermometer in the water, stirs the water, measures the initial temperature of the water, use the clock to find the time taken for the water to cool by 5 degrees Celsius and by 10 degrees Celsius, repeats the experiment 3 times, explain why the water is stirred before taking the temperature reading. You don't get any question easier than that. So the simple reason is so that the temperature of the liquid, or the temperature in this case, the liquid is water, the temperature of the water becomes uniform. So what I'm going to write is, to ensure temperature of the water is uniform. Doesn't get easier than that. Alright, now the student uses 200 cubic centimeter of hot water in the same beaker in each test. So he has changed the hot water into 200 cubic centimeter of hot water. Okay, state one other experimental variable that the student keeps constant to make a fair comparison of the 3 sets of results. For a fair comparison, if you have changed the volume, but you need to ensure that the initial temperature of this water should also be same. So same initial temperature. Only then we can have a fair comparison. Alright, the table shows the readings obtained by the student. And it says complete table 2.1 by calculating the average time taken for the water to cool by 5 degrees Celsius. Give your answer to appropriate number of significant figures, which in this case, for this one data, when you're finding the average, the appropriate number of significant figures would be 2SF, because the raw data is in 2SF. So 84 plus 82 plus 84 plus 82. 82 plus 84 plus 82 divided by 3. There were 3 values, and the average would be, in this situation, you simply hit it on the calculator, 82.67, which in 2SF would be 83. So if you write 82, you get 1 mark, 82.6, you get 1 mark, 82.7, you get 1 mark, because the second mark is for appropriate number of significant figures. Anyway, suggest one reason why the time taken for the water to cool by 10 degrees Celsius is not double the time taken for the water to cool by 5 degrees Celsius. So let's say what they're saying is, when the temperature of the water decreased by 10 degrees Celsius, why is not the time double for when the temperature of the water was decreased by 5 degrees Celsius? And the simple reason is because the rate of cooling of the liquid, or the rate of cooling, depends on the initial temperature as well. The more the initial temperature, the rate of cooling would seem to be faster, because there would be more difference between the temperature of the water and the room temperature. And when the temperature of the hot water drops, it approaches to pretty much the same as room temperature, the rate of cooling would slow down. And eventually, if the temperature of the water reaches, let's say, 25 degrees Celsius, and the room temperature was also 25 degrees Celsius, at this stage, there would be no heat transfer because the thermal equilibrium is reached. So the rate of cooling would be faster when the initial temperature was higher. So the reason is the initial temperature not as the initial temperature. Alright, you can write any one of these two sentences. I'm just writing the second one for an option, as the initial temperature of water is closer to room temperature. Alright, comparatively closer to room temperature compared to what it was at the start. Alright, anyway, moving on to the next one. The student repeats the experiment using 250 cubic centimeter beaker. All the experiment variables are same, and then he obtains the data that he plotted in the table. Describe the rate, describe the difference in the cooling of the water in the two beakers. Refer to the results recorded in table 2.1 and table 2.2 in your answer. So in the first five, the temperature decreases by 5 Celsius in this case in 110 seconds. Previously, it took 83 seconds. And it decreased by 10 degrees Celsius in 250 seconds. Previously, it was being decreased at 181 seconds. So if we compare the data, now it is taking more time for the temperature to be decreased. So it has slower rate of cooling. Well, it's taking more time. Slower rate of cooling. So cools at slower rate in the second beaker. Yeah. as it took more time for same temperature drop. Once again, equal to what, or compared to what? Compared to the water in the first container. And why is that? We have the same amount of water, all right? We are measuring it for the same drop of temperature. Why is the time different for the two containers? The answer is, let's say this is your container 1. You have 250 cubic centimeter of water in it. Then you might be having another container that is like this. It also have 250 cubic centimeter of water. In this one, the rate of cooling would be higher, but it has more surface area that is exposed to the air. And in this one, the rate of cooling would be slower. It has less area that is exposed to the air. Different surface area of the two containers. Right, of water. So here we have a student measures the density of a sample of modeling clay. The clay is molded into a cube as shown in figure 3.1. The first one, part A, suggests one difficulty the student finds when molding the clay into the cube. So for the cube, he has to make it a 3D shape, kind of a box, and all the sides should be of the same length. Must be having the same dimension. So when we are doing with the modeling clay, one of the difficulty is the very same one. Now it would be difficult for him to ensure that all the sides have the same length. So we can write for this one. Difficult to ensure same length for all sides. So all the sides must be having the same length, same dimension. All right, then we have the next one. On figure 3.1, measure the length d of one side of the cube. So you can see from here, all you have to do is put your ruler over here in front of it and measure the distance till this point. So might be a little bit different when we do on the sheet of paper. The answer can be a little bit different from the answer provided in the marking scheme. When we paint it on a sheet of paper, somehow the dimensions are kind of changed. Sometimes they are magnified, sometimes they are diminished. So anyway, what is the answer for the value of d? 2.4. Yeah, it is 2.4. It's just exactly the same. Okay, very well. 2.4 centimeters. We had to measure in centimeters. Calculate the volume of the modeling clay using the equation. and the volume of the cube is length times length times length, or the cube of the length. The length in this case is represented by d, so that would be the cube of 2.4. We just hit it on the calculator.
$13.82.
13.82. So I'm leaving it with one decimal place. That'll be enough. Alright, then we have the next one. The student uses a balance to find the mass m of the modeling clay as shown in figure 3.2. And then the mass is shown. We have calculated the volume. We gotta put all these put both the values in the formula and calculate the value of the density. So 36.3 divided by 13.8. That's the value for the mass. Mass was in grams and the volume was in cubic centimeter, because we'll need to write the unit as well.
2.6.
2.6 grams per cubic centimeter. This was kind of an easy one. Just we had to record some of the values and plug it into the formula and do some calculations. Anyway, moving on to the next one. A student investigates. This one is about the circuits and stuff. The student investigates the current in the resistor of fixed resistance. The following apparatus is available: ammeter, electrical connecting leads, the wires, a resistor of fixed resistance, lamp, switch, variable resistor, 6-volt battery, LED, voltmeter. Okay, this is the apparatus that is available. Anyway, the first part is state which piece of the apparatus is used to measure the current. Kind of an easy one. The current is measured in amperes. The unit is ampere, and the device is called ammeter. Alright, then we have the one for the 3 marks, in which we have to draw the circuit. The student measures the current for a range of potential differences. Mean he's changing the voltage. Changing the value of V, potential difference or voltage. Draw a circuit diagram to show the circuit that the student uses. You may use all or some of the apparatus available. Alright, so we're not going to use all of them. We can use a power supply, and then we'll need to change the power supply, so we can use a variable resistor and the fixed resistor obviously should be there, because we have to measure the potential difference across it. Then we need to have the ammeter in series. Yeah, so stuff like this. and measure the current for a different range of potential differences. So we have variable resistor and a switch. Okay, so what I'm going to do is I'm going to use the ammeter from here. Ammeter, the wires would be used obviously. Resistor of the fixed resistance. I can use the switch. 6-volt battery. Variable resistor to change the resistance. Alright, so starting off with the 6-volt battery. Here we have this one. Then we have the switch. Here's the switch. And then I can connect the ammeter anywhere in the series, in series with the circuit, means with the resistor. So here's the ammeter. Then I have the variable resistor. This is a variable resistor by which we can change the voltage across the fixed resistor. And here's the fixed resistor. Yeah, here's a fixed resistor, and then we complete the circuit. So the value of current would be actually measured through the ammeter. So variable resistor. This one is fixed resistor. Then we have the battery. Here we have the switch. And here it is the ammeter. And how are we going to use it for a different range, for a range of potential differences? You see, they ask us to measure the amount of current for a range of potential differences. So we're going to change the resistance of this variable resistor, and that would change the resistance of the fixed resistor, and then we can measure the amount of current passing through the fixed resistor. Alright, describe how the student obtains different values of potential difference across the fixed resistor. Like we explained it already, that he can adjust the value of the variable resistor. So by adjusting the value of the variable resistor, he would obtain different values of potential difference across the fixed resistor. And if we really want to get into the theoretical concept here, so let's say the battery is providing 6 volts. The battery is providing 6 volts, it's mentioned over there. If I want, let's say, and the fixed resistance is of, let's say, 500 ohm, right? And I want 3 volts over here. Then the variable resistor, I have to adjust the variable resistors in such a way that its resistance is exactly the same, 500. Then I'll be getting the equal share of the voltage across the variable and across the fixed resistor. The voltage would be divided equally. If I want less voltage across this one, let's say I want only 1 volt over here, then I have to increase the value of the variable resistor, and by increasing the value of the variable resistor, more share of the battery's voltage would be given to the variable resistor, and only the fraction of the voltage of the battery would be given to the fixed resistor. So you can change the value of the voltage that you need according to your need by adjusting the value of the resistance of the variable resistor. Sorry, variable resistor.